Since humanity raised its sight toward the stars, we have dreamed of converting ourselves into an intergalactic species, exploring the vast cosmic oceans that extend beyond our home galaxy. Hollywood has painted epic futures where we navigate between galaxies, as if they were islands in a celestial archipelago. But there exists a devastating truth that science has revealed, and that the majority of us do not want to accept. We will never ever abandon the Milky Way. This is not a temporary limitation that future technology will solve. It is not an engineering challenge waiting to be overcome by more advanced civilizations. It is a definitive sentence pronounced by the fundamental laws of the universe itself, a cosmic prison of 100,000 light-years in diameter, from which we will never escape. Tonight, in Nocturnal Science, we will explore the most unsettling reality that our species faces. We are destined to be eternal prisoners of our own galaxy. If you find it fascinating to discover the deepest and most disturbing truths about our cosmic destiny, accompany us on this nocturnal journey, where science reveals limits that no human ambition will ever be able to surpass. Incomprehensible distances. What would happen if I told you that the distances between galaxies are so incomprehensibly vast that they make interstellar travel seem like a walk in the park in comparison, and that these distances represent an absolute barrier that no technology will ever be able to surpass? Humanity has dreamed for millennia of exploring the stars, but there exists a devastating truth that few dare to contemplate. We are trapped forever on a cosmic island called the Milky Way. When we contemplate the night sky, we see thousands of stars that seem to be dispersed throughout the universe. We are really seeing is only an infinitesimal fraction of our own galaxy, a local cosmic neighborhood that represents less than 1% of the stars that make up our Milky Way. Even the most distant stars that we can see with the naked eye are relatively close to us, at a few hundred or thousand light-years of distance. The implications of these galactic distances transcend any technological limitation that we have faced as a species. We are not talking about engineering challenges that future generations will be able to solve with better rockets or more efficient energy sources. We are confronting fundamental limits imposed by the very structure of space-time, barriers that will remain impassable no matter how much human civilization advances. But here is where reality takes a turn that completely changes our perspective on the destiny of humanity in the cosmos. The distances that separate us from other galaxies are not simply large, they are so monumental that they defy any frame of reference that we could use to understand magnitudes. They are cosmic abysses that convert our galaxy into a perpetual prison from which we will never escape. The scale of our confinement. To understand the magnitude of our cosmic confinement, we must begin with the dimensions of our own galactic prison. The Milky Way has approximately 100,000 light-years of diameter and contains between 200,000 million and 400,000 million stars. Each one of these stars could have planetary systems, worlds that could harbor life, civilizations that could be looking toward us at this very moment. 100,000 light-years might sound like a manageable distance, until we consider what it really means. Light, traveling at the fastest speed physically possible in the universe, takes 100,000 years to cross our galaxy from end to end. Our fastest spaceships, like the Voyager probes, travel at speeds that are minuscule fractions of the speed of light. Voyager 1, launched in 1977, has traveled for more than 45 years and has barely exited our solar system, at its current speed of approximately 17 km per second. It would take more than 72,000 years to arrive at Proxima Centauri, our closest neighboring star, and that is only to reach the first star outside our solar system. To completely cross our galaxy at the speed of the Voyager, we would need approximately 2,000 million years. That is almost half the age of the Earth. By the time a ship launched today reached the opposite edge of the Milky Way, our sun would have converted into a red giant, would have engulfed the inner planets, and would have transformed into a white dwarf slowly cooling down, the intergalactic abysses. But these numbers pale in comparison with the distances to other galaxies. Andromeda, our closest neighboring galaxy and the only large galaxy visible to the naked eye from Earth, is located approximately 2.5 million light-years away. This distance is 25 times greater than the complete diameter of our own galaxy. To put this distance in a perspective that can resonate with our human experience, let us consider a scaled analogy. If the Earth were the size of a marble of 1 cm in diameter, our galaxy would have approximately 1,000 km of diameter on this same scale. Andromeda would be located at a distance of 25,000 km. It is as if we were on a marble in Madrid, and Andromeda were another marble located at the other extreme of the planet. But even this analogy does not completely capture the immensity of the problem. Between our Earth marble and the Andromeda marble there is nothing. Except almost absolute vacuum. There are no cosmic service stations, there are no intermediate planets where to refuel, there are no friendly civilizations that can offer assistance. It is an ocean of vacuum so vast that the very concept of travel becomes almost meaningless. The Triangulum galaxy, another relatively close neighbor, is at approximately 3 million light-years of distance. The brightest galaxies that we can observe with telescopes are at tens or hundreds of millions of light-years. Most distant objects that we have detected are at more than 13,000 million light-years, so far away that their light began its journey toward us when the universe had barely a fraction of its current age. These distances are not merely large. They are so extraordinary that they transcend any evolutionary frame of reference that our brains have developed to process magnitudes. We evolved to navigate distances of kilometers, or, in the best of cases, continents. Intergalactic distances operate on scales that are literally beyond human intuitive comprehension. Permanent cosmic loneliness. The immensity of these distances also reveals something profound about the nature of the cosmos. We are fundamentally alone on intergalactic scales. Any civilization that might exist in Andromeda could be so advanced as to have completely dominated its galaxy. But for us, they would remain as inaccessible as if they existed in a completely separate parallel universe. This cosmic loneliness is not temporary. It is permanent and absolute. It does not matter how much time we wait. It does not matter what technological advances we achieve. It does not matter how intelligent or determined future human generations become. Intergalactic distances will remain as absolute barriers that define the eternal limits of our cosmic domain. The realization of this intergalactic loneliness fundamentally transforms our understanding of what it means to be an intelligent species in the cosmos. We are not potential explorers of an infinite universe. We are permanent inhabitants of a finite cosmic island, surrounded by oceans of vacuum that we will never be able to cross. In nocturnal science, we explore these cosmic truths that challenge our most ambitious dreams, but that reveal the fundamental nature of our place in the universe. And this revelation about the absolute limitations of intergalactic exploration has awakened in you a fascination for the cosmic limits that define our existence. I invite you to continue this nocturnal journey, where we will discover that the barriers are even more absolute than we could imagine. The distances between galaxies are not simply technical obstacles waiting to be overcome. They are fundamental characteristics of a cosmos that has involuntarily designed perfect prisons for intelligent civilizations. We are conscious prisoners in a jail of light of 100,000 light-years in diameter, and intergalactic distances guarantee that this prison is eternal and inescapable. The immensity of the cosmic ocean that surrounds us is not only a measure of distance. It is a measure of our fundamental loneliness in a universe that is both vaster and emptier than our ancestors could have ever imagined. We are alone. We are confined, and the laws of physics guarantee that we always will be. The absolute barrier of the speed of light. In the most optimistic corners of the human imagination, we often fantasize about spaceships that can accelerate indefinitely, reaching speeds that would allow us to explore distant galaxies on the timescales of a human life. This fantasy feeds on decades of science fiction that has painted a future where the speed of light is simply another technical limit waiting to be surpassed by advanced engineering. But there exists an inexorable physical reality that shatters these dreams. The speed of light is not only a speed limit. It is an absolute barrier incorporated into the fundamental structure of the universe itself. The speed of light in a vacuum. Exactly 299,792,458 m per second. It is not arbitrary. It is not a technical limit imposed by the limitations of our current engines. Temporary restriction that future technology will overcome. It is the maximum speed at which any information, energy or causal influence can propagate through space-time. It is literally the maximum speed of the universe. Einstein taught us that nothing with mass can reach the speed of light, because doing so would require infinite energy. This is not a poetic exaggeration. It is a precise mathematical declaration about the nature of physical reality. As a massive object accelerates and approaches the speed of light, its relativistic mass increases exponentially, requiring increasingly astronomical amounts of energy for each additional increment of speed. The energetic implications of attempting to reach significant relativistic speeds are so monumental that they defy any concept of technological feasibility. To accelerate even a small spaceship the size of a house up to only 90% of the speed of light, you would need energy equivalent to the total energy production of the sun during several years. To reach 99% of the speed of light, the energetic requirements shoot up to levels comparable with the energy contained in entire stars. But even if we could magically solve the energetic problem and build ships capable of traveling at 99.99% of the speed of light, The numbers for intergalactic trips remain devastatingly discouraging. A trip to Andromeda, our closest neighboring galaxy, would take approximately 2.5 million years, according to observers on Earth, even at this almost luminal speed. Relativistic time and absolute one-way trips. Relativistic time dilation provides a small theoretical consolation for hypothetical travelers. Due to the effects of special relativity, the passengers of a ship, traveling at 99.99% of the speed of light, would experience the trip to Andromeda as a trip of barely 20 subjective years. For them, the trip would be relatively brief and feasible within a human life. However, this apparent solution creates an even deeper and more disturbing problem. While the travelers experience only 20 years of personal time, 2.5 million years would have passed on Earth when they finally arrived at Andromeda. All the human civilization that they knew would have disappeared millennia ago. The Earth would have experienced evolutionary, geological, and even astronomical changes that would make their home world completely unrecognizable. If they decided to return immediately, they would experience another 20 subjective years of travel, but they would arrive at an Earth that has aged 5 million years since their original departure. The human species, as we know it, could have evolved towards something completely different, having become extinct or having transformed into life forms that transcend any category that we can imagine currently. This temporal differential converts any intergalactic trip into an absolute one-way trip, not only in spatial terms, but also temporal ones. The intergalactic travelers would convert into permanent temporal exiles, disconnected forever from any civilization or culture that they had known. They would be explorers condemned to the most absolute and imaginable cosmic loneliness. The impossible energetic requirements. The energetic requirements for relativistic propulsion also reveal the practical futility of such enterprises. Energy necessary to accelerate a ship of 1,000 tons up to 99.9% of the speed of light would be approximately equivalent to the rest mass energy of the entire ship multiplied by a factor of more than 20. This means that you would need to convert directly into energy a mass equivalent to 20 times the mass of your spaceship. Even with perfect efficiency of conversion, mass energy, something that violates the laws of thermodynamics, you would need to transport 20 times more fuel than the mass of your ship. But since this fuel also must be accelerated, the energetic requirements become recursively impossible. It is a problem that no conceivable engineering can solve within the limits of known physics. The most exotic propulsion technologies that physicists have proposed theoretically face equally insurmountable limitations. Antimatter engines that represent the most efficient possible form of mass energy conversion would still require amounts of antimatter so vast that their production would demand the combined energy of entire stellar civilizations during periods of time that exceed human history. The concepts of solar sail propulsion, although elegant in their simplicity, face fundamental limitations of radiation intensity. To accelerate significant payloads to relativistic speeds using radiation pressure, you would need directional energy sources so intense that they would require engineering structures of stellar scale. We are talking about projects that would require dismantling entire planets to build lasers the size of solar systems. The concept of nuclear pulse propulsion, popularized by the Orion project in the decades of 1950 and 60, represents perhaps the upper limit of what we could achieve with technologies based on known physics. These ships would use sequential nuclear detonations to generate thrust, potentially reaching speeds of up to 10% of the speed of light. But even these extreme speeds remain pathetically inadequate for intergalactic distances. A trip to Andromeda using nuclear pulse propulsion would take 25 million years. That is more than 5 times the duration that hominins have existed on Earth. By the time such a ship arrived at its destination, terrestrial evolution would have produced completely new species, possibly multiple times. Theoretical wormholes that capture popular imagination as possible shortcuts through space-time remain firmly in the realm of theoretical speculation without solid experimental basis. The mathematical solutions that allow traversable wormholes require exotic forms of matter and energy that we have never observed and that may not exist in physical reality. Even if such structures existed naturally, manipulating them to create practical travel routes would require engineering capabilities that transcend any conceivable technology. We are talking about directly manipulating the geometry of space-time at galactic scales. Projects that would require energies comparable to those contained in supermassive black holes. The speed of causality. The search for superluminal speed technologies faces even more fundamental obstacles. Special relativity not only prohibits speeds greater than light, It establishes that such speeds would create causal paradoxes that would violate the logical consistency of the universe. Objects that travel faster than light could in principle arrive at their destinations before departing, creating violations of causality that would break the ordered structure of spacetime. The speed of light is not simply an arbitrary speed limit. It is the fundamental speed of causality itself. It is the maximum speed at which causes can produce effects, the maximum speed at which information can propagate, the maximum speed at which any physical influence can extend across the cosmos. This understanding transforms the speed of light from a technical obstacle into a fundamental law that defines the very structure of reality. It is not something that we can overcome through more intelligent engineering. It is something with which we must live as a permanent characteristic of the universe in which we exist. The limits imposed by the speed of light also reveal something profound about the nature of the cosmos. It is involuntarily designed to keep civilizations isolated on intergalactic scales. The distances are so vast, and the maximum speeds are so limited, that intergalactic travel becomes not only difficult, but effectively impossible for any civilization based on ordinary matter. This realization places us in a unique and strange position in the cosmos. We are intelligent enough to understand the immensity of the universe, advanced enough to measure the distances to other galaxies, but fundamentally limited by the laws of physics to remain eternally confined in our galactic island. The speed of light thus reveals itself not as a temporary limit waiting to be overcome, but as an absolutely impassable barrier that defines the permanent limits of any civilization based on matter. We are prisoners of physics, confined forever within the limits of the Milky Way, by laws that are as fundamental as existence itself. This understanding radically transforms our perspective on the human destiny in the cosmos. We are not future conquerors of galaxies. We are permanent inhabitants of a single galaxy, eternally limited by the same physical laws that allow us to exist and contemplate the universe that we will never be able to completely possess. The expanding cosmic conveyor belt. Imagine for a moment that you are the strongest and most determined swimmer in the world, capable of maintaining speeds that defy human limits for indefinite periods. Now imagine that you attempt to swim upstream against a current that is not only faster than your maximum speed, but that constantly accelerates, becoming more intense with every passing second. No matter how hard you swim, no matter how much determination you have, no matter how long you persist, the current will inexorably pull you away from your destination. This analogy perfectly captures the despairing situation that faces any civilization that dreams of intergalactic trips in our universe. The cosmos is not a static stage where galaxies remain in fixed positions waiting to be reached by ambitious explorers. Instead, we live in a dynamic and expanding universe, where space itself is continuously growing, pushing galaxies away from each other at speeds that increase with distance. This cosmic expansion is not simply an additional obstacle for intergalactic travel. It is a fundamental barrier that makes such trips not only difficult, but literally impossible for the majority of cosmic destinations. The expansion of the universe was discovered by Edwin Hubble in 1929, when he observed that distant galaxies move away from us at speeds proportional to their distances. This observation, known as Hubble's law, revealed an extraordinary truth about the nature of the cosmos. Not only is it vast, but it is becoming vaster every passing moment. The implications of an expanding universe for intergalactic travel are devastating and absolute. While speed limitations impose severe temporal restrictions on cosmic trips, the expansion of the universe creates barriers that actively worsen with time. Not only are galaxies far, they are continually moving away, converting any intergalactic trip into a chase of targets that constantly move away. But here is where the situation becomes even more despairing, revealing a cosmic reality that transforms expansion from a challenging obstacle into an absolute prohibition. The expansion is not uniform nor constant. It is accelerating. A mysterious force known as dark energy is causing the rate of expansion of the universe to increase over time, pulling galaxies apart from each other at increasingly greater speeds. To completely understand the futility of intergalactic trips in an expanding universe, we must examine the specific numbers that govern this cosmic process. The Hubble constant, which measures the current rate of expansion of the universe, is approximately 70 km per second per megaparsec. This means that for every megaparsec of distance, approximately 3.26 million light-years, galaxies move away from us at an additional speed of 70 km per second. Andromeda, located at approximately 2.5 million light-years of distance, should be moving away from us at a speed of approximately 50 km per second due to cosmic expansion. However, Andromeda is a notable exception because it is gravitationally bound to the Milky Way as part of the local group of galaxies. Mutual gravitational forces dominate over cosmic expansion at these relatively short distances, which is why Andromeda is approaching us at approximately 110 km per second. But this local exception is deceptive and temporary. The local group, which includes the Milky Way, Andromeda, and several smaller galaxies, represents an island of gravitational stability in a cosmic ocean of expansion. Beyond the limits of our local group, cosmic expansion completely dominates, inexorably pulling away all other galactic structures. The galaxies in the Virgo cluster, located at approximately 54 million light-years of distance, move away from us at approximately 100 km per second due to cosmic expansion. This speed of recession is already significant compared with the maximum speeds attainable by any conceivable propulsion technology. At distances of 1 billion light-years, galaxies move away at speeds of approximately 20,000 km per second, close to 7% of the speed of light. At distances of several billion light-years, recession speeds approach significant fractions of the speed of light, at the observable limit of the universe. The most distant galaxies move away from us at speeds that approximate the speed of light itself. The cosmic event horizon. This acceleration of recession speed with distance creates what cosmologists call the cosmic event horizon. There exists a critical distance, approximately 16,000 million light-years from us, beyond which galaxies move away faster than the speed of light due to the expansion of space. Any galaxy beyond this horizon is permanently out of our causal reach. No matter how much time we wait or what technologies we develop, the existence of this cosmic horizon means that the majority of the observable universe is already causally disconnected from us. We can see these distant galaxies because their light was emitted billions of years ago when they were closer to us. But we will never be able to reach them because the space between us is expanding faster than any physical signal can travel. Dark energy, which represents approximately 68% of the total energy density of the universe, is accelerating this expansion. Studies of distant supernovae have revealed that the expansion of the universe not only continues since the Big Bang, but that it is accelerating. This acceleration means that the cosmic horizon is not static. It is shrinking from our perspective, over time. More galaxies will cross the cosmic horizon and disappear from our causally accessible universe. In approximately 100,000 million years, all galaxies outside our local group will have been swept away by accelerated expansion beyond our cosmic event horizon. Future astronomers in that epoch will live in a seemingly empty cosmos, with only the fused galaxies of the local group visible in their telescopes. This shrinking of the causally accessible universe reveals the temporary nature of our current cosmic opportunities. Not only are we limited by the speed of light and intergalactic distances, we are racing against a cosmic clock that is permanently closing travel routes to distant destinations. Even for galaxies that currently are within our causal horizon, cosmic expansion creates devastating additional challenges for any attempt of travel. A spaceship heading toward a distant galaxy not only must cover the initial distance, it must constantly overcome the additional distance created by continuous expansion during the trip. Let us consider a hypothetical trip to a galaxy located a billion light-years away. This galaxy moves away from us at approximately 20,000 km per second due to cosmic expansion, during the time that it would take for even light to travel to this galaxy. A billion years. The expansion would have pushed the galaxy away another additional 6,500 million light-years. A spaceship traveling at subluminal speeds would face an even more severe problem. While the ship travels toward its destination, the target galaxy continues moving away. For many distant galaxies, the speed of recession due to cosmic expansion exceeds any technologically feasible travel speed. It is literally impossible to reach these destinations because they move away faster than we can travel toward them. This situation is analogous to attempting to walk on a conveyor belt that moves in the opposite direction at a greater speed than your maximum walking speed. No matter how persistent you are, no matter how long you walk, you will never advance toward your destination. In fact, you will continuously move away from it. Accelerated expansion also means that this situation constantly worsens. Galaxies that currently could theoretically be reached by ships traveling at significant fractions of the speed of light will eventually move away so fast that they will become unreachable. The number of accessible cosmic destinations is constantly decreasing. Some cosmologists have speculated about the possibility that advanced civilizations could harvest galaxies, pulling them gravitationally before expansion pushes them away permanently. However, Such projects would require capacities of gravitational manipulation at scales that transcend any conceivable technology. We are talking about moving entire galaxies. Objects that contain hundreds of billions of stars and have masses equivalent to trillions of times the mass of our Sun. Cosmic expansion also reveals the temporary nature of our current cosmic moment. We live in a unique epoch in the history of the universe, where we can observe distant galaxies and contemplate the structure of the cosmos on a grand scale. The future inhabitants of our universe, after accelerated expansion, has pushed away all distant galaxies beyond the horizon. We'll have a much more limited view of the cosmos. This temporal perspective adds urgency to our current scientific efforts to understand the universe. Not only are we spatially limited by cosmic expansion, we are temporally limited. The window of opportunity to study the cosmos in all its observable glory is gradually closing. The understanding of cosmic expansion radically transforms our concept of the human destiny in the universe. We are not simply limited by static distances and maximum speeds. We are competing against a cosmos that actively moves away from us. It is as if the universe conspired to keep civilizations isolated, creating barriers that are not only difficult to overcome, but that become more difficult with every passing moment. The expansion that eternally pushes us away thus reveals another layer of our cosmic confinement. Not only are we trapped by speed limitations and vast distances, we are swimming against a cosmic current that constantly accelerates, pushing our potential destinations away faster than we will ever be able to travel toward them. In this cosmic race against the expansion of space-time, we have already lost before beginning. The universe itself is moving away from us, converting our dreams of intergalactic exploration into eternally lost chases against targets that constantly fade into the expanding cosmic distance. The invisible executioner, dark energy. In the darkest corners of the cosmos lurks a force so mysterious and powerful that it constitutes more than 2/3 of all that exists in the universe and nevertheless is completely invisible and undetectable, except by its devastating effects on the destiny of all civilizations. This force, known as dark energy, is not simply another obstacle for intergalactic travel. It is the cosmic executioner that is actively executing the death sentence of any dream of exploration beyond our local group of galaxies. Dark energy represents 68% of the total energy density of the universe, amply surpassing both ordinary matter and dark matter combined. It is a form of energy that uniformly permeates all space, exerting a negative pressure that causes space itself to expand at an accelerated rate. But unlike all other known forms of matter and energy that tend to attract gravitationally, dark energy has the opposite effects. It repels, expands, and separates. The most disturbing thing about dark energy is not only its omnipresence, but its inherently anti-civilizational nature. While gravity unites stellar systems, galaxies, and galactic clusters, creating the organized structures that allow the formation of planets and the evolution of life, dark energy works tirelessly to undo these structures, pulling everything away from everything else with a relentless determination that transcends any possible technological resistance. The implications of living in a universe dominated by dark energy are so profound that they completely redefine what it means to be an intelligent civilization in the cosmos. We are not simply facing temporary technical limitations that future generations could overcome through more advanced engineering. We are confronting a fundamental force of the universe that is actively working to guarantee our permanent cosmic isolation. But here is where the situation becomes truly despairing, revealing a cosmic reality that transforms dark energy from an interesting scientific phenomenon into an existential threat for any intergalactic ambition. Dark energy not only causes expansion, it is accelerating that expansion in a way that worsens exponentially with time, creating a cosmic future where our isolation will become increasingly absolute. The discovery of cosmic acceleration. Arrived through studies of distant supernovae in the 1990s, astronomers expected to find that the expansion of the universe was gradually slowing down due to the mutual gravitational attraction of all cosmic matter. Instead, they discovered the opposite. The expansion was accelerating, propelled by this mysterious dark energy. This acceleration means that the recession speeds of distant galaxies are not constant. They are continuously increasing. A galaxy that today moves away from us at 20,000 km per second will move away even faster tomorrow and even faster the day after. It is as if the universe were continuously applying more energy to separate us from our potential cosmic destinations. The effects of dark energy are subtle on local scales, but dominant on cosmic scales. Inside our solar system, inside our galaxy, and even inside our local group of galaxies. Gravitational forces are strong enough to resist the effects of dark energy, but beyond these scales, dark energy completely dominates, dictating the destiny of every cosmic structure. This scalar dominance of dark energy creates a cruel hierarchy of cosmic accessibility. Close objects remain gravitationally bound and potentially accessible, while distant objects are inexorably dragged out of our reach. It is as if the universe had deliberately created concentric circles of isolation, allowing local interactions while prohibiting broader cosmic connections. The nature of dark energy also reveals why no conceivable technological solution exists for this problem. Unlike speed limitations or energetic barriers, which in principle could be overcome by sufficiently radical advances in physics and engineering, dark energy is an intrinsic property of spacetime itself. It is not something external that we can avoid or overcome. It is the fundamental structure of the physical reality in which we exist. To attempt to defeat dark energy would be equivalent to attempting to change the fundamental laws of physics. You would require not only energy sources of cosmic scale, but the capacity to directly manipulate the geometry of spacetime across volumes that span billions of light years. We are talking about engineering projects that would require total control over the structure of the universe itself. Dark energy is also accelerating what cosmologists call the Big Rip or cosmic Great Tear. In this scenario, which could occur in approximately 20,000 million years, dark energy will eventually overcome all other fundamental forces, including the nuclear forces that hold together subatomic particles. Much before this final apocalypse, however, dark energy will have effectively completed our cosmic isolation in approximately 100,000 million years. All galaxies outside our local group will have been pushed away by accelerated expansion beyond our cosmic event horizon. For the future inhabitants of our local cosmos, the universe will seem to contain only a massive galaxy, the eventual fusion of the Milky Way and Andromeda. This shrinking of the observable universe means that we are living during a unique temporal window in cosmic history. We are perhaps the only generation that will be able to observe the structure of the universe on a grand scale in all its glory. Future astronomers will have a much more limited and deceptive view of the cosmos, potentially leading them to incorrect conclusions about the fundamental nature of the universe. Dark energy also means that any civilization that manages to survive during cosmological periods of time will face a destiny of growing loneliness. Not only will they be unable to reach other galaxies, they will eventually lose even the capacity to observe them. The cosmos will become progressively emptier and more isolated from their perspective until they finally exist in a universe seemingly devoid of any structure beyond their own galactic island. This temporal perspective of growing isolation adds a deeply disturbing existential dimension to our cosmic confinement. Not only are we trapped spatially, we are being progressively more isolated. Temporally, the accessible universe is constantly shrinking, converting our current cosmic moment into an epoch of privileged observation that will never repeat. The omnipresence of dark energy also reveals something fundamental about the inhospitable nature of the cosmos for ambitious civilizations. The universe is not simply indifferent to our dreams of intergalactic exploration, it is actively hostile to them. Dark energy works tirelessly to undo any cosmic connection, separating potential civilizations and guaranteeing that they remain eternally isolated in their respective galactic islands. This cosmic hostility is not intentional, of course, but its effects are so systematic and complete that they could seem deliberate. It is as if the universe had been designed specifically to prevent contact between civilizations, creating barriers that are not only difficult to overcome, but that reinforce themselves automatically with time. The constant density of dark energy, as the universe expands, presents another disconcerting characteristic of this mysterious force. While ordinary matter dilutes as space expands, dark energy maintains a constant density. This means that as the universe grows, the total amount of dark energy increases proportionally, providing increasingly more fuel for the acceleration of the expansion. This self-reinforcing characteristic of dark energy means that the effects of cosmic isolation can only worsen over time. There exists no natural mechanism that can slow down or reverse the effects of dark energy. It is a fundamentally unidirectional force that pushes the universe towards states of increasingly greater separation and isolation. Theoretical attempts to manipulate or counteract dark energy would require forms of exotic matter and energy that might not exist physically. Even if such exotic forms of matter were possible, controlling them and applying them at cosmic scales would require technological capabilities that transcend any realistic concept of advanced civilization. Dark energy thus reveals itself as the most insidious and absolute enemy of any intergalactic ambition. It is not simply an obstacle to be overcome. It is a fundamental characteristic of the universe that guarantees our permanent confinement. It works silently, invisibly, but relentlessly to separate all cosmic structures, creating a future where galactic loneliness is not only inevitable, but progressively intensifies. This understanding transforms our perspective about our place in the cosmos from temporarily limited explorers to permanent prisoners of forces that are completely beyond our control or influence. Dark energy does not respect ambitions, does not recognize determination, and cannot be negotiated or overcome. It is the cosmic force that has sealed our destiny as eternal inhabitants of a single galaxy in a universe that becomes increasingly emptier and lonelier. The invisible enemy, which is dark energy, represents the final victory of the cosmos over any civilization that aspires to transcend its galactic limits. It's the force that guarantees that we remain forever as observers of a universe that we will never be able to possess, explorers of a galaxy in a cosmos that moves eternally away from our reach. The delusion of advanced propulsion. In the most advanced laboratories of Earth and in the most brilliant minds of the scientific community, engineers and physicists have conceived propulsion technologies that seem taken directly from the most optimistic science fiction. Antimatter engines that convert mass directly into energy with perfect efficiency, solar sails the size of continents that harness the pressure of stellar radiation, nuclear pulse propulsion systems that utilize controlled thermonuclear explosions to generate thrust. These technologies represent the absolute pinnacle of what we could achieve if we completely mastered the laws of known physics. However, when we apply these most exotic and advanced technological concepts to the realities of intergalactic trips, we discover a devastating truth that destroys even our most ambitious dreams. Even the most miraculous technologies that we can conceive within the limits of known physics are pathetically, almost comically inadequate to overcome the distances that separate us from other galaxies. It is like attempting to cross oceans on a surfboard or climb mountains with stepladders. Antimatter engines represent theoretically the most efficient possible form of propulsion, converting matter directly into energy. According to Einstein's famous equation, E equals mc2, when matter and antimatter mutually annihilate, they convert 100% of their combined mass into pure energy, an efficiency that no other known physical process can match. This perfect efficiency has led many space enthusiasts to consider antimatter propulsion as the definitive solution for high-speed space travel. But even with this theoretically perfect efficiency, the numbers for intergalactic trips remain absolutely prohibitive. To accelerate a spaceship of 1,000 tons up to 10% of the speed of light using antimatter propulsion, you would need approximately 45,000 tons of antimatter as fuel. This means that your ship of 1,000 tons would require 45 times its own mass in the most exotic and difficult to produce fuel of the universe. The production of antimatter presents challenges that transcend any realistic concept of industrial feasibility. The most advanced particle accelerators in the world can produce antimatter only at a rate of a few nanograms per year, and this requires enormous amounts of energy. To produce 45,000 tons of antimatter using current technology would take more time than the age of the universe and would require more energy than that produced by all human civilization in its complete history, even if we could magically solve the problem of antimatter production. The challenges of storage and safe manipulation present equally insuperable obstacles. Antimatter cannot enter into contact with ordinary matter without instantaneous annihilation, requiring magnetic or electrical confinement systems that consume energy continuously. Any failure in these systems would result in the most devastating explosion conceivable, releasing energy equivalent to thousands of hydrogen bombs. Solar sail propulsion systems, although elegant in their conceptual simplicity, face even more severe limitations when scaled for intergalactic speeds and distances. These ships would utilize enormous sails to capture the radiation pressure of intense light sources, converting photons into mechanical thrust. To accelerate significant payloads to relativistic speeds, you would need sails with areas of millions of square kilometers and directional energy sources of unimaginable intensity. The construction of such sails would require lighter and stronger materials than anything that currently exists, deployed in structures that would surpass the size of entire planets. The energy sources necessary to propel these gigantic sails would require lasers or particle beams with powers equivalent to the total energetic production of entire stars focused with perfect precision across distances of light years, even if we could build such systems. Solar sail propulsion faces fundamental physical limitations related to beam dispersion and the decrease of intensity with distance. The power available to accelerate the ship decreases with the square of the distance from the energy source, which means that the effective acceleration reduces rapidly as the ship moves away from its system of origin. Project Orion, conceived in the 1950s and conceptually developed during the following decades, represents perhaps the most promising approach for ultra-high-speed propulsion, using completely known and proven physics. This system would use sequential nuclear explosions detonated behind a massive spaceship, utilizing the impulse of these explosions to generate thrust across a gigantic pusher plate. The most optimistic designs of Project Orion could theoretically accelerate spaceships up to approximately 10% of the speed of light. An extraordinary speed according to conventional propulsion standards. However, even this extreme speed remains completely inadequate for intergalactic distances. A trip to Andromeda using Orion propulsion would take approximately 25 million years. 25 million years represents a period of time that transcends any realistic concept of civilizational continuity. To put this period into perspective, the first hominins appeared on Earth only some 7 million years ago, all the history of the human species. From our primate ancestors to modern civilization, spans a period less than the time necessary for a single intergalactic trip, using the most advanced propulsion technology conceivable. Nuclear fusion propulsion systems, although more feasible than antimatter in terms of fuel availability, offer significantly lower energetic efficiencies. Fusion converts approximately 0.7% of the fuel mass into energy, compared with the 100% of theoretical efficiency of matter-antimatter annihilation. This means that fusion engines would require approximately 140 times more fuel than antimatter engines to achieve the same speeds. Fusion reactors also face monumental technical challenges related to the confinement of plasma at temperatures of hundreds of millions of degrees, the management of intense neutron radiation, and the maintenance of sustained reactions in the hostile environment of deep space. After decades of intensive research, humanity has not yet managed to create fusion reactors that produce more energy than they consume. Theoretical wormholes popularized by science fiction as convenient shortcuts through spacetime remain firmly in the realm of mathematical speculation, without solid experimental basis. The solutions of Einstein's equations that allow traversable wormholes require exotic forms of matter with properties that we have never observed and that might not exist in physical reality, even if wormholes were physically possible. Manipulating them to create practical travel routes would require engineering capabilities that transcend any conceivable technology. We are talking about directly manipulating the geometry of spacetime, creating and maintaining stable tunnels across additional dimensions, and controlling energies equivalent to those contained in supermassive black holes. The concepts of superluminal speed, like the warp drives popularized by Star Trek, face even more fundamental obstacles. These theoretical systems would require exotic forms of matter with negative energy densities that would violate known energy conditions. Even if such forms of matter existed, the quantities required to create significant warp effects would be equivalent to the mass energy of entire stars. The manipulation of spacetime at the scales necessary for superluminal propulsion could also create devastating causal side effects, including temporal paradoxes that would violate the logical consistency of the universe. Objects that travel faster than light could in principle arrive at their destinations before departing, creating causality violations that would break the ordered structure of cause and effect. Propulsion systems based on exotic electromagnetic fields like M-drive engines, which have generated controversy in the scientific community, have not demonstrated violating the laws of momentum conservation in reproducible and reliable ways. Even if such systems worked as proposed, the forces generated are so small that they would be irrelevant for high-speed propulsion. The devastating reality is that all conceivable propulsion technologies within the limits of known physics are fundamentally inadequate for intergalactic trips on time scales that have any meaning for biological civilizations. Even the most exotic and advanced technologies that we can imagine fail by orders of magnitude when confronted with the realities of intergalactic distances. This technological inadequacy is not a temporary limitation that smarter future generations will be able to overcome. It is a manifestation of fundamental limits imposed by the laws of physics themselves. The energetic requirements for intergalactic propulsion scale in ways that eventually collide against absolute physical barriers, such as the total amount of energy available. In entire stellar systems, the search for revolutionary propulsion technologies must also confront the fact that fundamental physics is extraordinarily well understood and proven in the energetic regimes relevant for space propulsion. Unlike earlier periods in the history of science, when new physical discoveries regularly opened completely new technological possibilities, Modern physics has reached a level of completeness that makes conceptual revolutions that could fundamentally change our propulsion capabilities unlikely. The technological limits that we face for intergalactic trips are not simply engineering challenges, waiting to be resolved by brighter minds or more abundant resources. They are manifestations of fundamental limitations incorporated into the very structure of the physical universe. They present the point where human ambition meets the immutable reality of natural laws. This understanding transforms our perspective about the technological destiny of humanity from unlimited optimism to acceptance of absolute limits. We are not simply a civilization temporarily limited by our current technology. We are a species permanently confined by physical limits that no conceivable engineering can overcome. The absolute technological limits for intergalactic trips thus reveal the cruel nature of the cosmos. It allows us to understand the immensity of the universe, while simultaneously denying us forever the capacity to completely explore it. We are technological prisoners in a cosmic jail, capable of seeing, but never of touching the galactic treasures that shine eternally beyond our reach. Milkomeda, the inevitable fusion. There exists a cosmic event programmed to occur in approximately 4,500 million years, which represents both our only opportunity for intergalactic expansion and the final confirmation of our eternal confinement in the local cosmos, the Milky Way and the Andromeda galaxy. These two gigantic islands of stars separated by 2.5 million years, light of almost absolute vacuum, are destined to collide and fuse in a cosmic dance that will last billions of years and create a new hybrid galaxy that astronomers have already baptized as Milkomeda. This imminent galactic fusion might initially appear as an expansion of our cosmic horizons, an opportunity to finally access the stellar treasures of another galaxy without the need to undertake the impossible trips that we have explored. But the reality of this cosmic event reveals something much more sinister and definitive. It will be simultaneously our only experience of intergalactic growth and the final seal of our permanent isolation from the rest of the observable universe. The collision between the Milky Way and Andromeda is not a speculative possibility or a distant hypothetical scenario. It is an astronomical event as inevitable as tomorrow's sunrise. Confirmed by decades of precise observations of Andromeda's movement toward us, astronomers have measured that Andromeda approaches our galaxy at a speed of approximately 110 km per second, overcoming local cosmic expansion due to the mutual gravitational attraction between the two most massive galaxies of our local group. The implications of this inevitable galactic fusion transcend any event that humanity has experienced or can imagine. We are talking about a process that will fundamentally reorder the structure of the local cosmos, creating new stellar systems, destroying others and altering the orbits of hundreds of billions of stars in chaotic patterns that will determine the destiny of innumerable potential worlds during the next billions of years. But here is where the nature of this galactic fusion reveals its profoundly ambivalent character, transforming what could seem like an expansion of opportunities into a confirmation of even more absolute limitations. The Milky Way Andromeda fusion will not provide us access to new cosmic territories to explore. It will simply reorganize our local prison environment into a different configuration, but equally confining. To completely understand the implications of this galactic fusion, we must examine the physical processes that will govern this monumental cosmic event when two galaxies collide. It is important to recognize that we are not talking about violent crashes between solid objects. Galaxies are composed principally of empty space, with stars separated by distances so vast that direct stellar collisions will be relatively rare during the fusion. However, the gravitational forces involved in this galactic fusion will create tidal effects that will dramatically distort the shapes of both galaxies. The characteristic spiral arms of the Milky Way will be stretched, deformed, and eventually destroyed. Enormous streams of stars will be expelled toward intergalactic space, creating diffuse structures that could persist for billions of years. The fusion process will occur in multiple phases over the course of several billions of years. The first close encounter, programmed for approximately 4,500 million years in the future, will significantly distort both galaxies, but will not result immediately in complete fusion. Instead, the two galaxies will pass next to each other, exchanging energy and angular momentum before temporarily moving away. During the following billion years, mutual gravitational forces will cause the galaxies to return for additional encounters, each one more destructive than the previous. With each close pass, more stars will be displaced from their original orbits, more galactic structures will be distorted, and more orbital energy will be dissipated through complex gravitational interactions. The final fusion, completed approximately 7,000 million years from now, will create a massive elliptical galaxy. That will contain all the stars previously belonging to both the Milky Way and Andromeda. This new Milkomeda galaxy will be significantly more massive than any of its progenitors and will have a completely different structure dominated by more random stellar orbits instead of the organized spiral patterns that characterize our current galaxies. The destiny of our solar system during this galactic fusion represents a fascinating uncertainty, but a relatively minor one in the broader cosmic context. Computer simulations suggest that there exists approximately a 10% probability that our solar system will be completely expelled from the fused galaxy, converting into a rogue system, drifting through intergalactic space, if our solar system remains within the fused galaxy, which is the most probable result. It will experience a completely altered orbit around the new galactic center. The Sun could find itself much closer or farther from the galactic nucleus, experiencing different levels of cosmic radiation and different frequencies of close stellar encounters. However, it is crucial to recognize that these local orbital changes, however dramatic they may be from our perspective, will not fundamentally alter our situation of cosmic confinement. Whether our solar system remains inside Milkomeda or is expelled to intergalactic space, we will continue being equally incapable of reaching other distant galaxies. In fact, the galactic fusion will occur precisely when dark energy is reaching its most complete dominance over cosmic structures. During the billions of years that it takes to complete the Milky Way Andromeda fusion, the accelerated expansion of the universe will have pushed all other galaxies significantly beyond our cosmic event horizon. By the time Milkomeda reaches its final configuration as a stable elliptical galaxy, the rest of the observable universe will have effectively disappeared from our sight. The galaxies of the Virgo cluster, currently visible with moderate telescopes, will have been pushed away by cosmic expansion to the point where not even the most powerful conceivable instruments will be able to detect them. This synchronization between local galactic fusion and global cosmic isolation is not coincidental. It is a manifestation of the fundamental temporal scales that govern the evolution of the universe. The gravitational forces that hold together local structures operate on the same temporal scales that dark energy needs to completely dominate cosmic dynamics. The future astronomers of Milkomeda. Future astronomers who live in Milkomeda will experience a radically different cosmos from the one we observe today. For them, the universe will seem to contain only one galaxy, their own. They will have no observational evidence of the existence of other galaxies, other galactic clusters, or the large-scale structure of the cosmos that we currently consider fundamental for our understanding of the universe. This limited future perspective will create profound challenges for the development of precise scientific cosmology. Without the capacity to observe other galaxies as cosmic laboratories to test theories about galactic formation and evolution, future scientists will have a much more limited empirical base to understand the fundamental physical processes that mold the cosmos. The loss of cosmic perspective will also have profound philosophical implications for future civilizations. The sense of cosmic scale, the humility that comes from recognizing our place in a vast universe populated by innumerable other galaxies, will be replaced by a more limited and potentially anthropocentric vision of the cosmos. In a certain sense, the inhabitants of Milkomeda will experience a return to a cosmic version of the pre-telescopic perspective, when humans believed that the universe consisted only of our local solar system. But this observational limitation will not be due to primitive technology. It will be a fundamental and immutable characteristic of a cosmos that has expanded beyond its capacity for observation. The Milkomeda fusion also marks the end of any theoretical possibility. No matter how remote that future civilizations could harvest other galaxies, pulling them gravitationally before cosmic expansion permanently pushes them away. By the time Milkomeda forms, all other significant galactic structures will be causally disconnected from us by the accelerated expansion of space. This temporal finality adds urgency to our current scientific efforts to understand the cosmos in all its observable glory. We are perhaps the only generation in the history of the universe that can simultaneously observe the large-scale structure of the cosmos and understand the physical processes that govern it. This window of observational opportunity is permanently closing. The cruel irony of the destiny of our prisoner galaxy is that we will experience our only intergalactic expansion, precisely when the rest of the universe becomes permanently inaccessible. We will gain access to the stars of Andromeda exactly in the moment when we lose forever any possibility of reaching any other cosmic structure. This fusion represents both the culmination and the termination of our possibilities for cosmic growth. Milkomeda will be our final galaxy, our complete and permanent cosmic domain. After its formation, there will be no more possible expansions, no more new horizons to reach, no more cosmic territories to explore, the inevitable destiny of our prisoner. Galaxy thus reveals the fundamentally limited and temporary nature of our cosmic opportunities. We will live a unique era of transition, where we will observe both the fusion of our local domain and the permanent disappearance of all that exists beyond it. In approximately 7,000 million years, when Milkomeda reaches its final stable configuration, we will have reached our definitive cosmic state. Inhabitants of a single massive galaxy in a seemingly empty universe, possessors of all the stellar resources of our local group, but eternally disconnected from any other structure in the observable cosmos. This will be our final cosmic inheritance. Not explorers of an infinite universe, but custodians of a finite galactic island in an expanding ocean of vacuum that extends eternally in all directions, carrying away with it any dream of connection with the innumerable other islands of light that once populated our observable cosmos. In the observatories of the distant future, when our species has evolved beyond recognition or has been replaced by forms of intelligence that we can barely conceive, the astronomers of Milkomeda will look toward the night sky and will see something that would fill us with existential horror. A seemingly empty cosmos where only one galaxy exists. For these future scientists, the concept of other galaxies will be as alien and mystical as dragons or unicorns are for us today. This transformation of future astronomical perspective will not be the result of some cosmic cataclysm or destructive event. It will be the natural and inevitable consequence of living in a universe where dark energy has completed its work of cosmic isolation. The most powerful telescopes that these future civilizations can build, instruments that perhaps surpass current capabilities by unimaginable orders of magnitude, will detect nothing beyond their own fused galaxy. Imagine the perplexity and the conceptual limitations that these future astronomers will face. They will develop theories about the formation and evolution of galaxies, basing themselves on a single example, their own. They will study galactic dynamics, the distribution of dark matter and processes of stellar formation, without the comparative perspective that we consider fundamental for modern scientific understanding. The implications of this observational limitation transcend mere technical restrictions to become fundamental obstacles for the development of a precise scientific cosmology. Without the capacity to observe multiple galaxies in different evolutionary stages, these future scientists will have enormous difficulties to understand the processes that gave shape to their own cosmic environment. But here is where the situation becomes truly unsettling, revealing how cosmic expansion not only deprives us of physical destinations, but also of fundamental knowledge about the nature of the universe. These future astronomers will develop cosmological models that will be necessarily incorrect and incomplete, not for lack of intelligence or sophisticated instruments, but because the observable universe will have been so dramatically reduced that the necessary evidence for precise cosmology simply will no longer exist. The erased cosmos. The astronomy textbooks in the distant future will describe a universe that consists of a single massive galaxy surrounded by infinite vacuum. Students will learn that Milkomeda represents the totality of material existence, that there are no structures beyond their home galaxy, and that intergalactic space extends empty and silent in all directions until infinity. This limited cosmic perspective will create profound challenges for the development of theories about the origins of the universe. Without evidence of other galaxies, without observations of the cosmic microwave background, which will have been redshifted beyond detectability, and without the capacity to study the large-scale structure of the cosmos, these future scientists will have a fundamentally deficient empirical base to understand how their universe came to exist. They might develop scientifically sophisticated creationist theories that will postulate that Milkomeda always existed in its current form, surrounded by infinite vacuum, without evidence of cosmic expansion or observable galactic evolution in other galaxies. The idea of a Big Bang in evolution could seem as speculative as astrology seems to us. The most creative scientists of these future civilizations could speculate about the possibility of other galaxies in distant regions of space. But their hypotheses would be impossible to verify experimentally. They would be relegated to the realm of speculative philosophy, not of empirical science. It is possible that some visionaries develop mathematically correct models of a cosmos populated by multiple galaxies, but without observational evidence. Such theories would remain as intellectual curiosities. The loss of cosmic perspective will also have profound implications for the development of fundamental physics in these future civilizations. Many of our most important insights about the nature of space, time and matter have come from studies of cosmic phenomena on a large scale. Gamma-ray bursts from distant galaxies, supernovae in other galaxies, the structure of the cosmic microwave background. Without access to these distant cosmic laboratories, future physicists will have to depend exclusively on local experiments and observations inside their own galaxy to develop theories about the fundamental laws of nature. This could result in a more limited understanding of phenomena that require cosmic scales to be completely understood. The absence of observable galaxies will also deprive future astronomers of the capacity to study supermassive black holes in a variety of galactic environments. While we can compare the behavior of central black holes in elliptical spiral and irregular galaxies, future astronomers will have access only to the examples inside Milkomeda. The programs of search for extraterrestrial life in the distant future will face even more severe limitations. While we can speculate about the possibility of civilizations in the billions of galaxies of the observable universe, future scientists will be limited to looking for life only inside their own galaxy. For them, the concept of extraterrestrial life will refer exclusively to other stellar systems inside Milkomeda. This restriction could lead to dramatically different estimates about the prevalence of intelligent life in the universe, without knowledge of the existence of billions of other galaxies, each one with hundreds of billions of stars. Future Drake equations will be based on stellar populations, orders of magnitude smaller than those we consider today. Future SETI programs will be inherently limited to looking for signals only inside Milkomeda. They will never be able to contemplate the possibility of civilizations in other galaxies simply because they will not have evidence that such galaxies exist. Their search for cosmic company will be confined to an infinitesimal fraction of the universe that we know contains potential life. Philosophy and religion in these future civilizations will also develop in fundamentally different ways due to their limited cosmic perspective. Questions about our place in the universe will have very different answers. When the known universe consists of a single galaxy, instead of hundreds of billions of galaxies, it is possible that they develop Milkomeda-centered cosmologies that grant their galaxy a special or unique status in the cosmos, without evidence of other galaxies as comparative context. They could naturally conclude that their home galaxy occupies a privileged or unique position in the structure of the universe. The historians of the future who study the ancient archives of our era could find our descriptions of a cosmos populated by multiple galaxies as fantastic as we find the medieval cosmologies of crystalline spheres. For them, our images from the Hubble Space Telescope, showing thousands of galaxies in a single visual field, could seem like imaginative works of art instead of precise scientific documents. This disconnection between preserved historical knowledge and present observational reality will create unique challenges for future academics. They will have to decide whether to trust ancient records that describe a much larger and populated cosmos, or in their own contemporary observations that show a seemingly empty universe beyond their galaxy. It is probable that they develop theories to explain this discrepancy, perhaps positing that the other galaxies described in ancient texts were erroneous interpretations of local phenomena, or that they represented some form of cosmological mythology developed by primitive civilizations that did not completely understand the nature of the cosmos. Future academic debates about the validity of historical astronomical records could divide the scientific community. Some could argue that the absence of observable galaxies indicates that they never existed, while others could propose that some unknown physical mechanism caused their disappearance or invisibility. Scientific education in these future civilizations will teach students that they live in a cosmos that consists of a single galaxy surrounded by infinite empty space. Introductory courses in astronomy will show images of Milkomeda as the totality of the known material universe, without any reference to other galactic structures. Advanced students who study observational astronomy will learn about the frustrating limitations of their most powerful instruments that can penetrate deeply into intergalactic space but detect nothing except vacuum and weak background radiation. For them, these observational limitations will be accepted as fundamental characteristics of the cosmos, not as consequences of cosmic evolutionary processes. The intellectual tragedy of these future astronomers is that they will live in a universe that is as rich, complex, and populated as ours. But they will have access only to an infinitesimal fraction of the evidence necessary to completely understand its nature. They will be competent scientists, working with dramatically incomplete data, arriving inevitably to conclusions that we would recognize as fundamentally erroneous. This perspective of the astronomical future reveals something profound about our privileged moment in cosmic history. Perhaps the only generation that can simultaneously observe the cosmos in all its structural glory and understand the physical processes that govern it. This window of observational opportunity is temporary and is permanently closing. The future astronomers without a universe thus represent the final destiny of all ambitious scientific search in a cosmos dominated by dark energy. No matter how intelligent they become, no matter what instruments they build, no matter what theories they develop, they will be eternally limited by an observational horizon that has been dramatically contracted by cosmic forces completely beyond their control. They will be heirs of a scientific legacy that describes cosmic wonders that they will never be able to see, students of a universe whose most important lessons will have become permanently inaccessible for direct observation. The paradox of cosmic knowledge. In the depths of the most advanced observatories of the world, where the most powerful telescopes ever built scan the confines of the observable universe, exists an irony so profound and cruel that defines the fundamental condition of any intelligent civilization. The more we learn about the cosmos, the more we understand the absoluteness of our limitations to explore it. We are like prisoners in a cell with perfectly transparent glass windows, capable of observing an infinitely beautiful outside world, but eternally condemned to remain separated from it by barriers that no amount of knowledge can break. This paradox of cosmic knowledge transcends simple technical frustrations or the temporary limitations of insufficient technology. It represents something much more fundamental and disturbing. The same physics that allows us to understand the nature of the universe simultaneously prohibits us from experiencing it completely. The equations that reveal the structure of the cosmos also reveal why that structure will remain forever outside of our physical reach. Every advance in observational astronomy, every improvement in our instruments, every refinement in our cosmological theories, provides us with clearer and more detailed views of destinations that we know with mathematical certainty that we will never be able to reach. It is as if the universe had granted us the capacity to understand its immensity, precisely so that we could completely appreciate the magnitude of our own limitation. The psychological and philosophical implications of this situation are extraordinary when examined completely. Unlike historical explorers who faced unknown oceans or unexplored territories, with the hope and expectation that they could eventually be conquered, we face a cosmos that we know intimately, but that we definitively know is beyond our reach forever. The ancient navigators looked toward distant horizons, not knowing what was beyond, but with the confidence that their ships could eventually take them to those unknown lands. We look toward distant galaxies, knowing exactly what is there, understanding their stellar compositions, their rates of star formation, their spiral arm structures, but simultaneously knowing that no ship that we can conceive will ever take us to them. This paradox manifests itself in particularly cruel ways in our most spectacular observational advances. The Hubble Space Telescope has shown us images of galaxies so distant that their light began its journey toward us when the universe had only a fraction of its current age. We can study these primitive galaxies, analyze their chemical composition, measure their rotation speeds, and even detect the formation of individual stars inside them. But every image that reveals more details about these distant galaxies simultaneously emphasizes their absolute inaccessibility. The more we know about them, the more completely we understand why we will never visit them. Knowledge and accessibility are inversely related. The more precise our observations become, the more definitive our limitations become. Future telescopes, like the James Webb Space Telescope and its even more advanced successors, will dramatically expand our observational capabilities, allowing us to see even further in space and time. We will be able to observe the first galaxies that formed after the Big Bang, study the atmospheric composition of exoplanets in distant stellar systems, and even potentially detect biospheric signatures that indicate the presence of life. Each one of these observational advances will be simultaneously a triumph of human knowledge and an additional confirmation of our cosmic confinement. We will be able to know that life exists on worlds located thousands of light years away, but we will also know with mathematical certainty that we will never be able to visit it, study it directly, or communicate with it in meaningful ways. The search for extraterrestrial life illustrates particularly well this cruel paradox of cosmic knowledge. Astrobiologists have developed sophisticated methods to detect life signatures in the atmospheres of distant exoplanets. They can identify chemical imbalances that indicate active metabolism, detect complex organic molecules that suggest biological processes, and even potentially identify technological signatures that indicate advanced civilizations. But the discovery of extraterrestrial life, especially intelligent life in distant stellar systems, would create one of the most frustrating situations imaginable for humanity. We would definitively know that we are not alone in the universe. But we would also know that we are permanently isolated from our cosmic companions by distances that no conceivable technology can overcome. This situation would be analogous to discovering radio signals from an advanced civilization on a planet orbiting a star. 100 light-years away, we could detect their transmissions, analyze their content, and even potentially decode elements of their culture and technology. But any attempt at two-way communication would take 200 years for a single exchange of messages, even if we could establish communication with such distant civilizations. The conversation would unfold on timescales that transcend the duration of individual lives or even entire civilizations. A single question and answer could require periods longer than all the history of human writing. It is communication that is technically available, but practically meaningless. Physics itself, which allows us to understand these limits, also provides us the tools to exactly calculate how insuperable they are. We can precisely determine how much energy would be required to accelerate spaceships to relativistic speeds. We can calculate the time dilation effects that travelers would experience, and we can predict how cosmic expansion would affect any attempt at intergalactic travel. These same equations that reveal the wonders of the cosmos also reveal its absolute prohibitions. Einstein gave us both the understanding that the universe contains billions of galaxies and the understanding of why we will never be able to visit them. General relativity simultaneously expanded our conceptual horizons and imposed absolute limits on our physical horizons. The development of quantum mechanics added another layer to this paradox of cosmic knowledge. We now understand that the universe operates according to principles that completely defy human intuition, with phenomena like quantum entanglement that allow instantaneous correlations across arbitrary distances. However, these same quantum principles prohibit the use of such correlations for faster-than-light communication or superluminal trips. Quantum information can be instantly correlated across the cosmos, but this correlation cannot be utilized to transmit useful information in ways that violate relativistic causality. It is like discovering that you have a telepathic connection with someone in another galaxy. But you can only use that connection to transmit random noise without informational content. Advances in observational cosmology have revealed that we live in a unique cosmological era where we can observe the structure of the universe on a large scale. Studies of the cosmic microwave background radiation have provided us a snapshot of the universe when it was only 380,000 years old, revealing the seeds of all subsequent cosmic structure. But these same observations also reveal that we are living during a limited temporal window of cosmic visibility. Accelerated expansion, propelled by dark energy, is gradually pulling distant galaxies beyond our observable horizon. Future astronomers will have access to much less information about the large-scale cosmic structure than we have available today. We are perhaps the last generation that can observe the cosmos in all its complete structural glory. This privileged perspective is temporary and is constantly eroding by cosmic forces that are completely beyond our control. Our current knowledge of the large-scale universe could represent the peak of possible cosmological understanding for any civilization. The detection of gravitational waves by LIGO has opened a completely new window to observe the cosmos, allowing us to listen to violent cosmic events like fusions of black holes and collisions of neutron stars. These detectors provide us information about phenomena that occur in distant galaxies, amplifying our understanding of extreme physical processes. But every detection of gravitational waves also confirms that these extraordinary events are occurring in locations that remain forever inaccessible for direct investigation. We can detect the fusion of supermassive black holes in galaxies billions of light-years away. But we will never be able to send probes to study the remains of such events. The programs searching for extraterrestrial intelligence face this same cruel paradox of cosmic knowledge. Detection methods become increasingly more sophisticated, capable of identifying increasingly subtler technological signatures at increasingly greater distances. But every improvement in our detection capabilities will simultaneously expand the volume of space where we could detect civilizations that we know we will never be able to contact in meaningful ways. The success of SETI, if occurs, will create the most frustrating and imaginable situation: definitive confirmation that we are not alone, combined with definitive confirmation that we are permanently isolated from our cosmic companions. It will be the most important discovery in human history and simultaneously the clearest demonstration of our fundamental limitations. The exploration of our own solar system illustrates another facet of this paradox of cosmic knowledge. sent robotic probes to all the main planets, landed on multiple moons, and studied asteroids and comets in extraordinary detail. Every mission reveals new wonders that expand our understanding of the diversity and complexity of planetary worlds. But even within our own solar system, we face limitations that reveal the scale of the intergalactic challenge. It takes more than 9 years for a spaceship to reach Pluto using current technology. Manned trips to Mars represent enormous technical and logistical challenges that we are barely beginning to resolve. If these relatively short trips within our own solar system are so challenging, intergalactic distances become completely absurd by comparison. The paradox of cosmic knowledge also manifests itself in our theories about multiverses and parallel universes. Modern theoretical physics suggests that our observable universe could be only a small part of a much larger multiverse, potentially containing infinite alternative versions of reality. These theories conceptually expand our horizons toward realms of possibility that transcend even our vast observable cosmos. But simultaneously, they establish that these additional realms of reality are even more completely beyond our reach than distant galaxies in our own universe. The final situation of humanity may be that of conscious cosmic prisoners, equipped with the knowledge to understand the infinite immensity of what exists beyond our reach, but confined forever within the limits of our local group of galaxies. We will be eternal observers of a cosmos that we can understand, but never directly experience. This cruel paradox of cosmic knowledge defines the fundamental condition of any intelligent civilization in a universe governed by the laws of relativity and dark energy. The more we know, the more completely we understand what we will never be able to know. Through direct experience, we are in the final analysis eternal students of a cosmic book, whose most fascinating pages will remain forever out of our reach, capable of reading about distant wonders, but never of visiting them, to understand, but never to experience, to know, but never to possess the infinite treasures of a universe that reveals itself completely to our instruments, while simultaneously denying itself forever to our bodies. The shrinking cosmic horizon. There exists an invisible border in the cosmos located at approximately 16,000 million light-years from Earth, which represents something more ominous and definitive than any prison wall ever built. This border is not made of solid matter, cannot be seen with telescopes, and does not exert any direct physical force on objects that approach it. However, it is absolutely impermeable and impassable, separating forever the regions of the universe with which we can interact causally from those that will remain eternally disconnected from us, no matter how much time we wait or what technologies we develop. This cosmic limit, known as the cosmic event horizon or Rindler horizon, is not static like a conventional physical wall. Instead, it is constantly shrinking from our perspective, progressively reducing the volume of the cosmos with which we can interact causally. Every second that passes, millions of galaxies permanently cross this invisible horizon, disappearing forever from our causally accessible universe and converting into cosmic ghosts that we can observe but never reach. The existence of this shrinking cosmic horizon reveals one of the most disturbing and counterintuitive characteristics of our universe. Not only are we spatially limited by distances and maximum speeds, but we are racing against a cosmic clock that is constantly reducing our opportunities of interaction with the rest of the observable cosmos. It is as if we were trapped in a room that shrinks progressively, where the walls inexorably approach toward us, constantly reducing the space available for our activities. The implications of living in a universe with a shrinking causal horizon transcend any limitation that we have considered previously. Not only are there places in the cosmos that we will never be able to reach, there are places that we are actively losing the capacity to reach destinations that could have been theoretically accessible in the past, but that become permanently inaccessible as time passes. But here is where the situation becomes truly despairing, revealing a characteristic of the cosmos that transforms our limitations from static challenges into a lost race against forces that constantly accelerate. The cosmic horizon is not shrinking at a constant rate. It is accelerating in its contraction due to the accelerated expansion propelled by dark energy, which means that we are losing causal access to regions of the cosmos at an increasingly greater rate. To completely understand the nature of this cosmic horizon, we must examine how it is defined and why it exists. The cosmic event horizon marks the maximum distance from which light emitted today could ever reach us in the future, taking into account the accelerated expansion of the universe. Beyond this distance, the expansion of space is occurring more rapidly than the speed at which light can travel toward us. This definition reveals something profoundly disturbing about the nature of expanding space. While we normally think of the speed of light as the absolute limit for any form of communication or causal influence, the expansion of space itself can exceed this speed limit. Space can expand more rapidly than the speed of light, because it is not information or matter moving through space. It is space itself growing. Galaxies located exactly on the cosmic event horizon move away from us at exactly the speed of light due to the expansion of space. Any galaxy beyond this horizon moves away more rapidly than the speed of light, which means that any signal that it emits today will never be able to reach us no matter how much time we wait. This absolute causal separation means that galaxies beyond the cosmic horizon have been effectively removed from the physically accessible universe. We can see many of these galaxies because their light was emitted in the past when they were closer to us, but we will never be able to interact with their current or future states in any way. The most unsettling aspect of the cosmic horizon is that it is defined not only by the current conditions of the universe, but by all the future history of cosmic expansion. A galaxy that is currently inside our causal horizon could permanently cross out of it if the expansion accelerates enough in the future. Once it crosses this horizon, it remains permanently disconnected from us, even if it is currently sending signals in our direction. Dark energy is causing this horizon to constantly shrink from our perspective. Galaxies that are currently at the limit of our causal reach are being progressively pushed beyond this limit by the acceleration of cosmic expansion. The volume of space with which we can interact causally is constantly shrinking like a sphere of influence that shrinks around us. Calculations based on our current understanding of dark energy suggest that approximately 94% of the observable universe, currently visible, is already beyond our cosmic event horizon. This means that we can see these distant regions because their light was emitted billions of years ago, but we will never be able to interact causally with them. In the distant future, when dark energy has completed its dominance over cosmic dynamics, our causal horizon will have shrunk to include only our local group of galaxies. All other cosmic structures, no matter how bright or massive they may be, will have been carried beyond our causal reach by the accelerated expansion of space. This contraction of the causal horizon is not a gradual process that occurs on distant cosmological timescales. It is happening now, every second of every day. While you read these words, thousands of galaxies are crossing our cosmic event horizon, converting forever into inaccessible parts of the cosmos, observable only as historical relics, whose light continues traveling toward us much after they have become causally disconnected. The cosmic horizon also reveals the temporal nature of our current observational opportunities. Future astronomers will have access to significantly less information about the structure of the cosmos on a large scale than we have available today. Many of the galaxies that we currently will study as examples of different morphological types and evolutionary stages will be completely unobservable for future civilizations. This progressive loss of observational information means that we are living during a unique cosmological era of maximum scientific opportunity. Never in the past has it been possible to observe so many distant galaxies and diverse cosmic phenomena, and never in the future will it be possible again. We are the lucky cosmic generation that exists during the peak of visibility of the universe. The effects of the shrinking cosmic horizon also extend to our capabilities of communication with potential extraterrestrial civilizations. Any civilization located beyond our cosmic event horizon is permanently uncommunicable with us. Not only can we not travel to them, we cannot exchange radio signals, we cannot coordinate activities, and we cannot collaborate on scientific projects. This absolute incommunicability means that the universe is fragmented into causally disconnected regions, each containing potential civilizations that remain eternally ignorant of mutual existences. It is as if the cosmos consisted of innumerable islands of causality, each completely isolated from all the others, by oceans of expanding space that no signal can cross. The search for extraterrestrial intelligence faces fundamental limitations imposed by this shrinking cosmic horizon. Not only are we searching for civilizations inside a finite volume of space, we are searching inside a volume that is constantly shrinking. Civilizations that could have been detectable in the past could have become permanently undetectable due to the contraction of our causal horizon. SETI programs of the future will operate inside increasingly smaller spheres of search, not due to technological limitations, but due to the fundamental reduction of the causally accessible cosmos. The probability of detecting extraterrestrial signals decreases not only because civilizations might be rare, but because the volume inside which such civilizations could be detected is constantly shrinking. The cosmic horizon also imposes limitations on our future capabilities to harness resources or energy from distant regions of the cosmos. Concepts of large-scale cosmic engineering, like Kardashev-type III civilizations, that harness the energy of entire galaxies, face the fundamental obstacle that the majority of galaxies are already beyond our causal reach. Even if we could develop technologies to manipulate matter and energy at galactic scales, we would be limited to working only inside our shrinking causal horizon. Truly cosmic engineering projects that span multiple clusters of galaxies or large-scale filament structures are impossible not only due to energetic limitations, but due to fundamental causal limitations. The existence of the shrinking cosmic horizon also has profound implications for our understanding of concepts like the universe and all that exists. Traditionally, when cosmologists speak of the universe, they refer to all space and time that emerged from the Big Bang, but from a practical and operational perspective, our accessible universe is only the region inside our causal horizon. This distinction between the total theoretical universe and the causally accessible universe will become increasingly important as our horizon continues to shrink. For practical purposes, the regions beyond our causal horizon could also be in completely separate parallel universes. Since we cannot interact with them in any physical way, future scientific research will be inherently limited by this contraction of the causal horizon. The physicists of the distant future will have access to significantly less data about the behavior of matter and energy in different cosmological conditions. Their understanding of the fundamental physical laws could be limited by the reduced range of observable phenomena inside their shrunk causal horizon. Future experiments in high-energy particle physics could depend on the observation of cosmic rays from extreme events in distant galaxies. Such galaxies have been carried beyond the causal horizon. These natural experiments will no longer be available for study. The contraction of the horizon limits not only our travel and communication capabilities, but also our scientific research capabilities. Astronomical education in the distant future will teach students about an observable universe that is dramatically smaller than the one we observe today. Textbooks will show cosmic maps that include only the structures inside the shrunk causal horizon, omitting the vast majority of galaxies and clusters that we currently consider standard parts of the observable cosmos. This educational reduction in known cosmological scope could lead to more limited and potentially erroneous scientific perspectives about the nature of the universe. Students will learn about a cosmos that appears significantly smaller, less diverse and less complex than what really exists beyond their shrunk observational horizon. The shrinking cosmic horizon thus reveals the inexorable, cruel nature of our confinement in a universe dominated by dark energy. Not only are we spatially limited, we are becoming progressively more limited with time. Our cosmic opportunities are not simply finite, they are actively shrinking, creating a form of cosmic claustrophobia where the walls of our spatial prison constantly approach. This understanding transforms our temporal perspective on cosmic exploration from patient optimism to existential urgency. We cannot simply wait for future generations to develop better technologies to explore the cosmos. Every moment we spend waiting permanently reduces the accessible cosmos. Time is not on our side. It is actively working against any ambition of cosmic exploration. The shrinking cosmic horizon represents the final victory of dark energy over any civilization that aspires to influence or explore the cosmos on a grand scale. Not only does it confine us spatially, it confines us temporally, guaranteeing that our cosmic future will be progressively more limited, more isolated and lonelier than our already restricted present. We are witnesses to the progressive contraction of our accessible universe, impotent observers of a process that is constantly reducing the scope of any cosmic ambition, gradually transforming a rich and diverse cosmos into an increasingly smaller and isolated bubble of existence that defines the absolute and eternal limits of any conceivable human future. A conscious custodianship. We have arrived at the end of our journey through the most devastating scientific reasons for which humanity will remain eternally confined inside the limits of the Milky Way. But in reality, we have arrived at a beginning. The beginning of a mature and realistic understanding of our true place in a cosmos that is simultaneously infinitely vast and infinitely inaccessible. We are in the final analysis conscious prisoners in a jail of light 100,000 light-years in diameter. Endowed with the intelligence to understand the immensity of what exists beyond our cosmic bars, but condemned forever to remain separated from it. This condition of conscious cosmic confinement represents something unique in the history of the known universe, unlike any other form of life that we can imagine. We have evolved until reaching a level of scientific understanding that allows us to map with extraordinary precision the exact limits of our galactic prison. We know the distances to other galaxies up to significant figures. We understand the forces that separate us from them, and we can calculate with mathematical certainty why we will never reach them. During our journey through the multiple layers of our cosmic confinement, we have discovered that every aspect of fundamental physics conspires to keep us permanently isolated in our galactic island. Intergalactic distances are so vast that they defy any evolutionary frame of reference that our brains have developed to process magnitudes. They are abysses of vacuum so monumental that they convert even our most ambitious interstellar trips into trivial displacements by comparison. The speed of light, that fundamental constant that defines the absolute limits of causality and communication in our universe, erects itself as an impassable barrier that no conceivable engineering can overcome. It is not simply a technical obstacle waiting to be resolved by smarter future generations. It is a limitation incorporated in the very structure of spacetime that will remain valid as long as the laws of physics exist. The accelerated expansion of the universe adds a cruel temporal dimension to our spatial confinement. Not only are we separated from other galaxies by unimaginable distances, these distances are constantly growing, pulling our potential destinations away faster than we will ever be able to travel toward them. It is as if we were swimming against a cosmic current that is constantly accelerating, converting us into participants of a race that we have already lost before beginning. Dark energy, that mysterious force that constitutes more than 2/3 of the total energetic content of the universe, works tirelessly as our invisible cosmic jailer. Not only does it cause the expansion of space, it is accelerating that expansion in ways that guarantee that our isolation will become progressively more absolute with time. Every second that passes, millions of galaxies cross permanently beyond our causal horizon, converting into cosmic ghosts that we can observe, but never reach. Even our most exotic and advanced propulsion technologies, from antimatter engines to nuclear pulse propulsion systems, fail pathetically when confronted with the realities of intergalactic distances. The energetic requirements for intergalactic trips scale in ways that eventually collide against absolute physical barriers, requiring energies equivalent to the total production of entire stars during periods that exceed the current age of the universe. The inevitable fusion between the Milky Way and Andromeda, programmed to complete in approximately 7,000 million years, will represent our only experience of intergalactic expansion. But this expansion will occur precisely when dark energy has completed its work of cosmic isolation, converting our fused galaxy into a solitary island in a seemingly infinite ocean of vacuum. Future astronomers who live in Milkomeda will face a dramatically impoverished cosmic perspective compared with ours. For them, the universe will seem to consist of a single galaxy surrounded by eternal vacuum. The concepts of other galaxies, large-scale cosmic structure, and the rich diversity of extragalactic phenomena that we consider fundamental to astronomy will be as alien to them as dragons or unicorns are for us. This future transformation of astronomical perspective reveals the cruel paradox of cosmic knowledge that defines our current condition. The more we learn about the universe, the more completely we understand the absoluteness of our limitations to explore it. We are students of a cosmos that reveals itself completely to our instruments while simultaneously denying itself forever to our bodies. The shrinking cosmic horizon adds existential urgency to our situation of confinement. Not only are we spatially limited, we are racing against a cosmic clock that is constantly reducing the volume of the universe with which we can interact causally, every passing moment. Our cosmic opportunities contract irreversibly. This understanding of our permanent cosmic confinement fundamentally transforms what it means to be an intelligent civilization. In the modern cosmos, are we temporarily limited explorers, hoping that future technology resolves our travel restrictions? We are permanent inhabitants of a specific region of the cosmos, confined forever by physical laws that are as fundamental as existence itself. The acceptance of this reality should not lead us to cosmic despair, but to a deeper appreciation of the extraordinary richness that exists inside our galactic limits. The Milky Way contains between 200,000 million and 400,000 million stars, each potentially accompanied by planetary systems that could harbor worlds as diverse and fascinating as anything that we could find in distant galaxies. Our confinement to a single galaxy is not a minor limitation when we consider the extraordinary temporal scale available for exploration, even traveling at significant relativistic speeds. Completely exploring all the stellar systems of the Milky Way would require periods of time that exceed by orders of magnitude all the history of life on Earth. The search for extraterrestrial life inside our own galaxy offers possibilities as rich and diverse as any intergalactic fantasy. If life is common in the cosmos, as many scientific estimates suggest, then the Milky Way could harbor millions or even billions of inhabited worlds, providing opportunities for discovery and exploration that could occupy humanity for eons. The technological challenges associated with interstellar exploration, although formidable, remain inside the realm of the physically possible using known scientific principles. Unlike intergalactic trips that violate fundamental limits of physics, interstellar trips represent extremely difficult, but not impossible, engineering problems that future civilizations could eventually solve. The prospect of becoming a truly galactic civilization, capable of traveling between stars and establishing presence in multiple stellar systems inside the Milky Way, offers a future grand and ambitious enough to inspire countless generations. Our confinement to a single galaxy does not diminish the magnificence of this potential destiny. In Nocturnal Science, we continue exploring these profound truths about our place in the cosmos, revealing both the absolute limitations and the extraordinary opportunities that define human destiny. And this journey through the scientific reasons for which we will remain eternally confined to the Milky Way has awakened in you a fascination for the limits and possibilities of human existence in the cosmos. We invite you to keep accompanying us in future nocturnal explorations where science reveals the deepest truths about the nature of reality. The understanding of our cosmic confinement also grants us a unique perspective on the precious rarity of our moment in the history of the universe. We are perhaps the only generation that can observe the cosmos in all its structural glory before accelerated expansion fragments it into causally disconnected islands. This observational window of opportunity is temporary and is permanently closing. Our status as conscious prisoners in a jail of light converts us into privileged witnesses of an extraordinary universe that we can understand, but never completely possess. This condition is not a motive for lamentation, but for celebration, because it grants us the unique capacity to appreciate both the immensity of what exists and the depth of our knowledge about it. The beauty of our cosmic situation resides in how it combines absolute limitation with extraordinary possibility. We are confined to a specific region of the cosmos, but that region contains riches sufficient to feed curiosity, exploration and discovery during periods of time that transcend any conceivable human scale. Future generations that inherit this knowledge about our cosmic confinement will have the advantage of realistic expectations about the scope of possible human exploration. They will not waste resources pursuing intergalactic impossibilities. Instead, they will be able to focus their ambitions on the extraordinary treasures that exist inside our accessible galactic limits. The mature acceptance of our cosmic limitations represents a milestone in the development of human wisdom. We have evolved from primitive ignorance about the scale of the cosmos through naive fantasies about unlimited exploration, to a sophisticated and realistic understanding of our true place in the architecture of the universe. This cosmic wisdom does not diminish our dreams. It focuses them toward objectives that are simultaneously ambitious and attainable. The destiny of becoming a galactic civilization extended across multiple stellar systems inside the Milky Way is a vision grand enough to inspire any intelligent species. Our permanent cosmic confinement also teaches us humility about our place in a universe that is much vaster and more complex than our ancestors ever imagined. We are an extraordinary species capable of understanding the fundamental laws that govern reality, but we remain subject to those same laws in ways that define absolute limits on our ambitions. In this final moment of contemplation about our cosmic destiny, we recognize that the confinement to the Milky Way is not a tragedy, but simply the reality of existence in a universe governed by relativity and dark energy. It is the natural condition of any intelligent civilization, advanced enough to understand the cosmos, but permanently limited by the laws that make that understanding possible. We are conscious prisoners. But our jailer is the same universe that endowed us with the capacity to contemplate its immensity. We are confined, but our confinement spans an entire galaxy of 100,000 light-years in diameter, containing treasures sufficient to feed exploration and discovery during periods that exceed human imagination. This is our cosmic heritage, not conquerors of an infinite universe, but conscious custodians of an extraordinary galactic island in an ocean of vacuum that eternally expands. It is a destiny that combines definitive limitation with extraordinary opportunity, creating the perfect conditions for a civilization that is wise enough to appreciate both what it can reach and what it must accept as eternally beyond its reach. We will remain forever in the Milky Way, and that permanence is not a limitation, but the very definition of our true and eternal cosmic home. No,